We'll talk about value model tuning. Value model tuning is about once you have predictions of tasks in a ranking from a ranking model in a recommender system. Value model is or multitask fusion describes the relative weights to give to the task predictions, and then you sort of combine them, compute a weighted sum of the predictions to get a single score for each task, and that is what you rank based on. So this is a very common approach used in modern recommender systems. So this is an example of a value model where I've sort of said that, hey, this is probably some sort of a video recommender system where you might have, let's say, 5 predictions from your ranking model, and these values here are the weights to multiply with these predictions. So, for instance, I've written here that the final score by which you're ranking is like 0.1 times this prediction plus 0.3 times this prediction, and so on and so forth. Okay, so we use value models, and normally what we do, by the way, there's some information on value models in this paper. There's a paper linked here and a previous article in our blog. Now, normally the way we optimize value models is some sort of search. So we change something and run an experiment and see if the result improves or not. And this is great, but I think somewhat based on my empirical knowledge of the field, I think what could be empowering is if practitioners, people who tune value model, if they had a tool to specify the desired importance of each task, and this tool sort of computes the value model weights from it. Now, I don't expect the weights output from this tool to just be perfect. You'll probably need to search locally around it, but this is a good way to jump to a point in your search space. Okay, so people use value models in recommender systems. It's a multi-dimensional search space. Usually, it's linear, and explainability is a big aspect of this. And here we are talking of how can we derive the weights of the value model from the desired importance of the tasks. And now, importance of the tasks, is it any easier to derive that? That's a separate question, and in my experience, it is. Separately, you can do a lot of analysis to figure out which tasks are more aligned with your business metric. So let's pretend for a second that the practitioners have a decent idea of the importance of different tasks, and from that we want to translate it into weights of the value model. Okay, so I'll go over 2 approaches, but we've also sort of written some code in GitHub repository, check value model tuning, and I'll go over some of these files. But, to set the context, we'll look at 2 approaches to this declarative value model tuning. One of them I'm calling Ndcg gap targeting, and the other is per task regret targeting. So briefly, the first approach is, I think there's a nice image here. Let me go to that. Ndcg gap targeting. Yeah. So briefly, the first approach is that we take, let's say right now, this W1, W2, W3, and here I'm pretending the 3 tasks. This is the current ranking, the current value model weights. So like I mentioned before, we will, for each of the items that you're ranking, we will compute a weighted sum. So W1 into this plus W2 into this plus W3 into this gets the first combined score. W1 into this, W2 into this, W3 into this gets the second combined score, and so on and so forth. So let's say based on the current weights, we compute a weighted sum of all the tasks and compute a base rank list. Now, if you remove one of these weights, like make one of them 0, and repeat your process, you'll get a new list. I'm calling that task ignored rank list. And there'll be, if you have t tasks, you'll have, from that you can get t different rankings. So what we are going to compute is the Ndcg, normalized discounted cumulative gain, I think, but basically a sense of how different these rankings are. So Ndcg is a measure, so we can compute the Ndcg between the base rank list and the task ignore rank lists. What this tells us is how much the ranking changes when you ignore the weight of this task. So if the weight of this task is very low, like say it was 0 to start with, then clearly the ranking will not change. So your task ignore rank list will be the same as your base rank list. Hence the Ndcg will be effectively 1. Ndcg is between 0 and 1. So Ndcg will be effectively 1. So the change in the Ndcg, which is 1 minus Ndcg, is going to be 0. So that is what I'm calling the gap. The gap in the Ndcg is the 1 minus the Ndcg between the task ignore rank list and the base rank list. Again, if the weight was already very low, then this gap will be close to 0. On the other hand, the weight is very high, let's say, I don't know, million or something, then clearly the task ignore rank list will substantially change from the base rank list. And, you should see a very large gap in Ndcg. So this motivates how we can compute a sort of Ndcg gap or delta to find what is the current importance of the task in the ranking. And what we do is we have, from the user, we have an input of what is the desired Ndcg gaps. It's not the actual value, but it's a relative. It's like a sum of values. Some of these desired gaps sums up to 1. So it's sort of a percentage, if you will. And once you have these desired ratios and you have the observed ratios, you can see which tasks have a smaller gap than what the user derives. If it's smaller, then you will need to increase the weight. And which tasks have a higher gap than what the user derives, which means you're affecting the ranking more than what the user wants to with this task. So the user actually wants to reduce the importance of this. So you will reduce the weight of this. So what I described right now is a heuristic approach to sort of a gradient of these weights. And that is what I've coded up in the Ndcg gap targeting heuristic. Let's go over the code. We're calling optimize weights with the data. The data contains the, here I've taken about 100 items and 5 task predictions for all items. And then I've said specified some desired Ndcg fractions. These are, I've just given sample inputs, but 0.3, 0.5, 0.7, 0.7, 0.06. As you can see, these sum up to a 1. And max iterations, learning rate, tolerance, for optimization. I have support for initial weights. I'm not doing anything fancy with it, but you can think of using it if you have a good guess or of where you want to start searching, then you can always plug it in. Okay, so now you call optimize weights. Optimize weights after some data transformation. And if the initial weights is none, then it sets it to equal. Then for the number of iterations, in each iteration, it computes your base scores, which you remember was a weighted sum of the predictions. So the data here is 100 rows of 5 like items per row, 5 columns, and weights. There are 5 weights. So this into this gives you base scores, which is 1 score per item. Then we are sorting based on that, and then for each of the tasks, we are setting that task to 0 to compute the task ignored score and task ignored ranking, right? So once again, if you remember, we had the original ranking, then we zeroed out one of the weights, we compute the task ignored ranking. So far so good. Then we'll compute the Ndcg between the base ranking and the task ignored ranking. And the one minus of these Ndcgs is the regret or the gap that we are creating by ignoring that task. And this step is to ensure that it's you divide by the sum. So these now sum up to 1. These are fractions. And then for each task you have a desired importance or fraction from it, and this is the observed. So the difference between them is now what you will act on the basis of. So once again, let's see the let's try to get an intuition of this optimization. Let's say the desired fraction of a task is 0.5. Okay, so we expect that it will substantially change, like almost half the Ndcg, half the sum of Ndcg gaps should come from this task, right? But maybe it's not. Maybe it's much less. Maybe the current Ndcg fraction of this task is, let's say, 0.2. So for that task, this will be a positive number. 0.5 minus 0.2, 0.2 will be a positive number, and it's reasonably big positive number. So in this case, diff is a positive number for that task, and learning rate times diff, learning rate is also a positive number. Learning rate times diff is a positive number. So we multiply the weight with 1 plus this quantity. So essentially, whatever the weight is, we are increasing it if the desired fraction is more than the current fraction. And this makes sense because if you increase the weight, that means this original base ranking is going to be affected more by this task. Hence, when you zero out the weight, you should create a bigger impact. So next time around, the next iteration, the difference should be lower for that task. So that's the iteration step, and we run this and then optimized weights. Just to show you that this works, run this heuristic, and for the desired fractions, Ndcg fractions, it came quite close. Okay, so we specify this is the Ndcg gaps, and it was roughly able to achieve that and gave us the value model weights, which you can plug back in and run your experiment or search nearby. Okay, so between the two tools I'm going to talk about, Ndcg gap targeting and regret targeting, I personally suggest starting with the Ndcg gap targeting. And as you can see, at least in this star example, he was able to achieve the reasonably close to the desired gaps. Now, I also tried to do the same with a black box optimization, SLSQP, which does not have the max iterations and stuff. It just calls minimize with the same objectives and stuff. Now, this is currently not working for me. I'm trying to figure this out, but as you can see here, it says optimization success true, terminated successfully, but it did not actually change the weights. So this is work in progress. Of course, this would be ideal if we can make this work. Why? Because this is this actually perturbs the weights, computes the gradient. It's just much more theoretically sound. But for now, I suggest people starting with the Ndcg gap targeting heuristic. Okay, so before I get to per task regret, so what we did here was that we were able to specify the relative importance, if you will, of different tasks, and we'll go back. We were able to specify the relative importance. We ran optimized weights. We got the value model base to try, which roughly achieves this Ndcg, this relative Ndcg gaps from the base ranking. Okay. Now, per task regret targeting is similar in spirit but slightly different. In this Google DeepMind paper, they say that I have an image for this. Imagine you take your task predictions and you rank only based on each of the tasks. So for the T tasks, you create T rank list only based on the predictions of that task. Okay, so clearly that ranking will be most optimal if the ranking corresponding to the task, the third task, let's say, will be best to, if you want to, if you only care about maximizing the observed value of task 3, right? So that's the optimal ranking for that task. Now your combined ranking, you can try to see what is the regret of the combined ranking from each of the task optimal ranking. So once again, we compute the T task optimal rankings, which just means ranking by just that task. And then we take the combined ranking based with the current weights, and we compute T Ndcgs, where we look at the current ranking against the T task optimal rankings. Now let's try to get an intuition of this. Now imagine your current ranking has a very low, like the gap from one of the Ndcg of this one with the second task, let's say, is very low. So that means the Ndcg of the current ranking with the task optimal ranking for task 2 is, let's just say, 0.98. It's close to 1. That means that it is almost able to achieve the same observed value of task 2 as if you were to rank only by the task itself. So your regret along task 2 is low. So you're not very worried about getting a lower observation of task 2 because your current ranking is doing a pretty good job. Like the best you could do is just by ranking by task 2, and the current ranking is actually very close. On the other hand, if the Ndcg is much below 1, then that would not be the case. You'll say, hey, there's a big gap between what my current ranking is doing and what I could have done if I had only ranked by that task. Right? So this approach we call regret targeting. It computes these regrets. We'll go over slowly. Runs the same number of max iterations, computes the current ranking. For each of the T tasks, it computes the Ndcg score of the current ranking against the base ranking, which is basically, which has been computed here once because you don't need to do it inside the iteration. This just ranks only by that task, right? So jth task in this case. So this is what what we were talking about earlier, that let's compute the Ndcg of the current ranking against a ranking of just based on that task. And 1 minus of that is the regret. Okay. Now we have a sense of how important this task is. Again, if the regret is high, but the importance of the task as specified with the user is low, then it's okay. Then we don't want to worry about this. Flip side, if the importance is high and the regret is high, then we do want to worry about this. So this is what we have sort of used to compute the gradient and update, and you can see the results here. It is roughly able to, this is a little harder to read, but it's roughly able to achieve low regret for the important tasks as specified in this example. So the example here, I specified the first 2 tasks as important and then the last 3 as less important. I should probably change the variable name here. It's more like, sorry, this last one, yeah, regret importances. First 2 tasks are important and the last 3 are less important. And the observed values of regret, it starts much higher for these 2, and it's able to move it down substantially and varies less above the last 3. Okay.